that tells you it's recording right there. All right, so I'm going to do number 1 over again here. So watch as I do this. If you already did it in your notes, you just follow along. You don't have to write any of this down. If you haven't done it yet, you should have done it already. But you would be wise to follow along and write this as part of assignment 1. So here's the data. Here's time, and here's velocity. And so the first thing it says is graph it. So here's number 1A. And let's go 1, 2, 3, 4, 5. And then it's to 15. Okay, and this is velocity in meters per second. So at 0, we have 0 velocity. At 1 second, we have 3, which 3 would be about right there, wouldn't it? And at 2 seconds, we're at 6. So 6 would be right about there. And then at 3 seconds, it's 9. And then 4, it's 12. And 5, it's 15. So it looks like. And so if you do the graphing paper, it should look something like that. Okay? Now it says write a mathematical model for this, so that's part B. And so you could say, well, y equals mx plus b. At some point we're going to stop doing that. But the vertical axis is velocity, and m is the slope. And I think it's pretty easy to see that each second we're going up by 3 meters per second. So, I mean, you can create whatever triangle you want. Here's 2, and this goes up 6. Here's from 1 to 4 is 3. It goes up 9. So, but however you divide it, you're getting you're increasing your velocity by 3 meters per second every second. And I'm going to leave it like that. You can also call it meters per second squared if you wish. The horizontal velocity is time. And then b, well, it goes through the origin, so that's just 0. So this is your answer right here. That's velocity as a function of time. Now we're going to do part C. We're going to use the area underneath the velocity versus time graph. And we're going to write a data table for the position of the car as a function of time. So, and we're going to assume that my starting position is 0. Remember we said the area underneath a velocity versus time graph represents your displacement. So this area, the area underneath this, well, the area underneath the whole thing here is, well, it's a triangle. So, I mean, if I went 15 meters per second for 5 seconds, that would be 75 meters, right? But a triangle, you're cutting it in half. So what's 75 divided by 2? Is that 37.5, I think? Is that right? Okay. So I end up going 37.5 meters total. But, you know, so anyway. So, but what I want to know is, as a function of time, how far have I gone? So I'll say this will be time in seconds. And this will be delta x in meters. But actually, since my starting position is at the origin, delta x is the same thing as x, because x initial is 0. 0, 1, 2, 3, 4, and 5. So now at 0 seconds, I haven't had any time to go anywhere. So my change in position is 0. And I said 0 is my starting position, so I'm at 0. Now at 1 second, well, I have velocity here. See here, this is at 3, but I started at 0. So I didn't really, if I go 3 meters per second for a second, I've gone 3 meters. But I haven't gone 3 meters. I've gone half of 3 meters. I've gone 1.5 meters. Does that make sense to everybody? Look at me. Okay? The area of this little is 1.5 meters. Now at 2 seconds, here's what I did on the last video. At 2 seconds, I treated this as a great big triangle, and I found the area of that, and that will work. The problem is that only works for this kind of problem, so I'm going to do it a little differently. This little triangle right here, I'm going to put its displacement. It represents 1.5 meters of displacement. But now, over the next second, see, how fast am I going at 1 second? I'm going 3 meters per second. Now, what if I went 3 meters per second without changing my speed? Well, I would go 3 meters, wouldn't I? If you go 3 meters per second for 1 second, that would be 3 meters. So this square right here, that area represents 3 meters of displacement. So what's the area here represent? Well, this is how much farther I went than 3 meters because I was going faster and faster. See here, I was going 6, but here I was going 3. So this is how far I went because this 3 meters right here represents how far I went because I already had some speed. And this is how much further I went because I increased my speed over that second. Now, how far have I gone total? 3 plus the 1.5 I already went plus the 1.5. Well, that's 3 plus 3 is 6 meters. Now, what I did last time is I just went, 2 times 6 is 12 divided by 2 is 6. So you get the same thing. Now, I'm going to do the third second here from here to here. Well, this is 6 meters per second right here for 1 second. So what does this all represent? 6 meters. You see that I went 6 meters during that second. Because I started off, I started that second going 6 meters per second. For 1 second, that would be 6 meters. But I also increased my speed. So this is 1.5 meters. So I started with 6. This all was 6. Plus 6 more, plus 1.5 more. So what is that? What are all these areas added together at 3 seconds? How far have I gone? 13.5 meters. And then here, this was 9. Okay. And then this is 9 meters, right? Because we start off the third second going 9 meters. We increase it to 12. So if I just went 9 meters per second for 1 second, I would increase my position by 9 meters, but I went 1.5 meters farther because I increased my speed during that second. So 9 plus 1.5, well, see, 1.5 plus the third, that's 15, and 15 plus 9 is 14. Is that right? So, 24, I mean? Is it 24? Yeah. Okay. And then you go from this last second, you start off going, what was it, 12. So this represents 12 meters, and this is 1.5 again. So 24 plus 12 is 36. 36 plus 1.5 is 37.5. And I'm done. So the idea here is to look at each second, figure out what the area is for that second, figuring out what the area, because that's my displacement that I went through for that second, but you add them up as you go along to get your total displacement from the beginning. Make sense? Now what we're going to do is we're going to graph, this is part D, we're going to graph the position as a function of time. And this graph has to be really big. Now I'm just going to draw this as a hand sketch right here, but in your notebook this should be at least half a page. I had one student yesterday, she made it like a full page, and they were fantastic. They were beautiful. It doesn't have to be a full page, but if it is, you know, you're going to get really good results for the next assignment. Well, 37, that's pretty close to 40, isn't it? So I'm going to go 20, 10, 30, and my zero position is 0. At 1, I'm 1.5. Well, here's 5. So 1, 2, 3, 4, 5. So 1.5, somewhere around there. Pretty low. At 2, it's 6. At 3, it's 13.5. Here's 15. 4 to 13.5, you're right about there. And then 4 is 24. And then 5 is 37.5, which is 3/4 of the way over, like that. And again, if you're using graph paper, this will be a lot nicer. Although this turned out pretty good. And notice, you get a nice curve. It's a parabola. We're going to show that it's a parabola mathematically later on. So you go from, you draw your velocity versus time graph, you develop a mathematical model for it, which we're not really using yet, but by looking at the areas underneath as we go, for each second I come up with a displacement and say, oh, one thing, delta x equals x minus x naught, or my final position minus my initial position, but I'm saying my initial position is 0. That's given. So therefore delta x is the same thing as just x, and that's why I'm just labeling this as my x, my position axis. I'm starting at the origin. You don't have to, it just makes it a little easier. Any questions? Okay, that is all.